Everyone, thank you very much for being here. For those who don't know me, my name is Ed Tipper. I have the pleasure of chairing the Climate Crisis Committee at St John's College, where we are today. And to introduce the event, I'm going to hand straight over to the Master of St John's College. Over to you.
Thank you very much. Thanks, Ed. Good evening, everybody. The warmest of welcomes to our Climate Crisis Lecture. And first of all, thank you to Ed and the committee for putting the event together. As many of you will know, St John's is working really hard to reduce our operational climate impacts. We're investing really heavily in schemes under our strategic master plan to significantly reduce our energy consumption and our carbon emissions. Passive house student accommodation, really fascinating and wonderful new biodiversity projects on the college estate. And these are all really meaningful and necessary steps to reduce our impact. But important as our commitment to those things is, without doubt, the biggest contribution that St John's is making to a viable future for our planet is fostering in our fellowship a research community which embraces the most extraordinary breadth and depth of exploration of climate and biodiversity crisis. That focus carries through to our postgraduates and to our research associates, and if you were here earlier, you'd have also seen our undergraduates who are hungry to make a contribution in this area. We heard from our summer research projects, our Mace Arnold research interns projects, and that's a programme organised by the Climate Crisis Committee and very generously funded by a Jonian donor. But we come together with this lecture with a particular purpose, and that is to bring to a wider audience that research and leadership in addressing the climate and biodiversity crises that's coming from our fellows and from our alumni. And by doing this, we hope to foster informed debate about its scientific, economic and policy dimensions and really harness collegiality and that disciplinary diversity that we can bring together. After this evening's lecture, Ed Tipper will invite some initial responses from two fellows of the college, Professor Laura Díaz Anadón and Professor Andy Woods, and then we'll open up the discussion to questions from the audience involving our speaker and panellists. And we'll wrap up with refreshments downstairs in the foyer. So, to our speaker. Professor Gideon Henderson, we're very proud to say, is an honorary fellow of St John's College. He is widely recognised as one of the UK's most senior scientific voices on climate and the environment, an internationally renowned geochemist whose research focuses on the carbon cycle, the oceans, and understanding the mechanisms that drive climate change. Gideon obtained his PhD here at St John's before moving to Columbia University, and then since 1999, basing himself at the Department of Earth Sciences in Oxford, where his positions have included serving as head of department. And Gideon's a fellow of University College, Oxford, too. In addition to his research work at that university, Gideon chairs the Met Office Science Advisory Committee. He's a senior independent member of the NERC Council and a member of the advisory board for the UN Decade of Ocean Science. He recently concluded 6 years as Chief Scientific Advisor and Director General at DEFRA, where he carried significant scientific influence across government, in addition to the weight that he brought to environmental policy and his area of specialism. Amongst Gideon's many accolades, and they are too many to list, but he is a Fellow of the Royal Society and of the Royal Society of Chemistry, which recognised him as leader in the field in 2023. So, Gideon, it is an absolute honour to introduce you as our 2026 Climate Crisis Lecturer and to invite you to deliver your lecture. Thank you.
Well, thank you very much for the invitation to be here, and thank you, Heather, for that wonderful introduction, slightly embarrassing introduction. It's great to share some of my thoughts today, and I'm going to talk about this subject, carbon dioxide removal, and try and bring in some of my thinking from a scientific and technical point of view, as well as my experience on the socio-economic and policy side. So we've known now for a long time, and there is political consensus in nearly every country, that we must do something to reduce our emissions of greenhouse gases to net zero during this century. We know we have to do it. We also know some of the technologies that we're going to use to do it. And one of them is shown by this no doubt very distracting, but I think rather beautiful image that I've just put up on the screen here. And that is to move away from fossil fuels, in this case moving away from coal energy. This is Didcot A power station. It used to keep the lights on in my home and my lab in Oxford. It no longer exists. And this was in 2014, it being destroyed. So we need to move away from this form of fossil fuel energy to systems that look rather more like this, and the renewable energy systems that are increasingly replacing electricity generation in our country. So the UK has been at the forefront of making these sorts of changes in our energy system. We lead amongst the G7 countries in terms of driving down emissions and have done for a long time. And this image here shows you the ways in which our different sectors in the UK have reduced emissions over the last few decades. On the left are the 6 big sectors, and you notice, for instance, the green on there of agriculture, something I worried about a lot when I was at DEFRA, and the stubborn failure to reduce emissions from agriculture through those decades. But you see greater successes. I'll focus perhaps on the right, first of all, some of the smaller sectors there amongst our fuel supply and our waste, and noticeable of all of them, the yellow curve on the left, showing the substantial decrease of emissions associated with electricity generation. Now, these are signs of some success, but it's getting ever harder to reduce these curves further towards the zero that we know we have to reach. If I take the yellow curve there, for instance, driving down electrical emissions, electrical energy production emissions, is becoming increasingly hard because we always need base load. We need dispatchable power that we can turn on and off when the wind doesn't blow or the sun doesn't shine. And that means that for the foreseeable future, we will continue to need gas or wood-fired power stations. And to do that, we really ought to be capturing the carbon from them and storing it underground. The only real alternative to dispatchable power is a substantial energy storage system. And both of those things, carbon capture and storage, or a substantial energy storage system, take a long time to build. You can't just knock them up overnight. You have to build them over some period of years and invest in the infrastructure. So driving down the yellow curve further is going to take some time. It's going to take investment in storage or CCS. And that's true for all of the things on these curves. Now we can formalize that understanding about how quickly you can change a system towards a low carbon system in something called an integrated assessment model, and that's what I show you on this now rather old figure here. What this is showing in black, let me see if I can get my pointer to work here. I just had a lesson on how I do it, so hopefully I can. There we are. What you can see in black on here is the historical emissions by year of greenhouse gas globally. And this is from a paper published in 2014, which was very influential in the Paris negotiations. The colour curves that extend beyond the historical emissions reflect what comes out of those integrated assessment models, our most detailed assessment of how quickly society might be able to change towards a low carbon future. And they're colour-coded basically by how quickly those scenarios are moving away from greenhouse gas emitting scenarios. And what you'll see on here notably is that the blue curves on here, the colour-coded ones that go low, reach the targets of Paris to keep our climate broadly around 2 or 1.5 degrees. But a notable feature that we see on these curves is that as you go through this century, they don't just reach net zero, but they cross the 0 point and they go to a place where we are removing more carbon dioxide from the atmosphere than we are emitting into it. And that's a substantive change in the system that we will have to follow if we're going to reach net zero and stabilise the climate at something below 2 degrees. So this figure shows you also, since 2014, where we've got to. And you can see that our climate policies have not been quite as bad as they would have been if we'd carried on as normal on the red curve here. We're here at that blue dot, but we are not down on the blue curve. And that means that the chances of following a trajectory from now that reach net zero and a stable climate will even more definitely require substantial carbon dioxide removal into future years. Now, this is a big challenge. I think that's a really important thing to recognise about the climate challenge. It's just the scale of the problem. You look at a graph like that, you can imagine it's a simple intellectual exercise, but it's not. It's an enormous engineering problem. And if you think about this from the emissions perspective here, this image already gives you a clue about this, the scale of our carbon emissions today is really huge. What does 40 gigatons, 40 billion tons of CO2 look like? That's the global emissions at the moment. I think it's quite nice to try and imagine what that looks like in the local context. If you take a cubic kilometre of coal, that's big, right, a cubic kilometre. A cubic kilometre of coal, that weighs about 1 billion tonnes of carbon. Okay? So if you think in Cambridge scale here, I think that a kilometre from here is down to just south of the Fitzwilliam Museum. And if you go the other way, I've forgotten what it's called, the Burley Arms on the Newmarket Road is almost exactly a kilometre east of here. So think about that scale of kilometre squared and a kilometre high. That's how much coal makes 1 billion tonnes. Okay, when you burn that much coal, CO2 weighs more than carbon, so it becomes about 4 billion tonnes in the atmosphere. But we're emitting 40 billion tonnes. So we need 10 of those cubic kilometres. That's the cubic kilometre on top of Cambridge up to the tropopause, 10 kilometres up where the planes fly. That's how much carbon we are taking every year, digging it out of the ground and putting it into the atmosphere to heat the planet. That gives you some sense of the scale of the change that we need to make. And the scale of the change that we need to make to carbon dioxide removal is also strikingly large. You see that in two good estimates, two reliable estimates made globally and in the UK and quoted up here. On the upper one from the state of carbon dioxide removal of something like 7 to 9 billion tonnes of carbon per year is thought to be required by 2050. So that's not the whole 10-kilometre stack, but that's 2 kilometres of your coal column every year that we need to be taking back out of the atmosphere, as well as reducing our emissions very significantly. In the UK, the percentage of change that we need to make is a little smaller. It's about 8% of our current emissions that we'll need to be withdrawing by 2050. And this is an estimate made for the Climate Change Committee, who don't just give us a sense of scale, but also of timing. They say we should be doing this really at scale in the next couple of years or starting, and also the technologies that we should be using: direct air capture, BECCS, weathering, and biochar. And those are 4 technologies that I'll touch on later on in the talk. But those are big numbers in either the global or national context in terms of how much CDR we are going to need to do. So I will come on and talk about the individual technologies and how they might work to achieve that. But let me first of all talk about the cost of doing this. A big engineering challenge like this is clearly going to be costly. And this is something which the Committee for Climate Change has indeed estimated for us. And this is shown on this cost abatement curve here, familiar sort of territory for economists in the room. And this shows you all of the different technologies that will need to be applied if we're going to reach net zero according to the Climate Change Committee's balanced pathway. So this is not just carbon dioxide removal, it's the whole lot. And you can see that some of those technologies actually save the economy money and can get us a long way. But if we want to go to net zero, we have to do some costly things too. And in black are the carbon dioxide removal technologies, which are the most expensive ways of getting to net zero. So clearly they are not an alternative to emissions reductions. We need to do all the colourful things on there first, but we also need to do carbon dioxide removal, but it will cost a lot of money. So how are we going to do it? How are we going to suckle this carbon out of the atmosphere? Now this is a figure that summarises the nature of the challenge and the various approaches that we can use. This is from a Royal Society report on the subject, which I chaired some years ago now. And the boxes on this figure have now filled up. I think there's more ideas. But the basic taxonomy of different removal technologies remains the same as in this Royal Society report. What we need to do is take greenhouse gases out of the atmosphere, and we can do that by biology, by accelerating inorganic reactions, or by engineering a system. And we need to put the carbon, having taken it out, somewhere where it'll stay permanently. And that can be into land vegetation, into dead vegetation, or into the oceans or our built environment. So I'm not going to go through all of the different technologies proposed on this table, but focus on a few of them and how useful they might be in achieving our goals. One thing I should tick off though straight away is most people, when they see this figure, they go to the top left and think, afforestation, yeah, that's great. Let's grow more trees. Surely that's a good thing to do. And it is definitely a good thing to do. We do need to grow more trees, but that's not going to be enough. Broadly speaking, what we've done to put CO2 in the atmosphere is burn a hell of a lot of fossil fuels and cut down a lot of trees. Just growing the trees again is not going to fix the whole problem. It just does a bit of it. And the other problem with trees, and you see that on this picture of a German forest here, is that trees are vulnerable. We see that from forest fires. We see it from the Eeps typographus, the bug that's eating these trees in Germany, that they are vulnerable to pests, fire, and drought. So trees are good, but we need to think about other technologies. And indeed, trees are often considered as part of land use change in climate discussions, not as carbon dioxide removal, and they don't feature in those very big numbers that I came up with earlier. So apart from trees, what are people trying? Well, pretty much anyone who's had a good idea about how you might take carbon dioxide out of the atmosphere has now started a company to try and do that. And these companies are being looked after and being traced and tracked by this rather nice website, CDR FYI, which lists all of the companies that are selling carbon credits for negative carbon, for taking carbon out of the atmosphere. So some summary things about the CDR market that CDR FYI tell us. So far, companies trying to buy credits have spent about 11 billion on the CDR market. Projections are that that will reach 100 billion in the fairly near future, 100 billion per year. The average CDR price at the moment, if you just look at how much is delivered versus how much has been spent, is about $260 per tonne. It's expensive compared to emissions trading schemes. But actually, the striking thing here is only 2.5% of those sold emissions have actually been delivered. We've worked out how to take out very little of this promised carbon. And that means that at the moment, the cost for taking carbon out of the atmosphere is about $10,000 per tonne. Rather an expensive technology. You have to hope that's really going to come down in the future. If we look at the overall number of companies, there's about 225 listed on this website at the moment. More than half of those have not yet delivered any CDR, and only 4 of them have delivered more than 100,000 tonnes of CDR so far. At that sort of scale of company, we're going to need more than 30,000 companies, equivalent to the biggest company in the market at the moment, if we're going to meet those carbon targets, and therefore if we're going to control climate. So we don't get a lot of companies, or some big ones in this market, we will not be able to control climate. That's something that's really worth remembering here. So let's think about what some of those companies are doing, how technically reasonable they are, and how scalable they might be if they're going to solve the climate challenge for us. So I'll focus on a few of those, and I'll start off by the 2 that are seen as the biggest potential in the UK market. So I'll start off with direct air capture and storage over on this side. It's an engineering approach. And shown schematically, what this approach does is simply build a machine to take carbon out of the atmosphere and then stick it underground. It's got some other arrows on here, but basically it's sticking it underground. So this is an entirely engineered solution to the problem. There are companies that are doing this. Oh, sorry, I should have said that on my slides here, what I'll try and do is for each technology, I'll show you the 3 biggest companies at the top of the slide which are currently doing this, and the scale of delivery of carbon dioxide removal that they've already achieved. So remember, what we're looking for is something like 8 billion tonnes a year by 2050. These 3 companies between them have done 1,600, not million or billion, just 1,600 tonnes. So compared to that column of coal, I don't know, this room is probably about 8 by 8 by 8 roughly metres. That's how big a cube is. 8 by 8 by 8 of coal is what they've done. So it's about a lump of coal the size of this room, compared to the size of the column that we need to suck out in the future. But good that they're doing it, and these are technologies that are doubtless going to be part of the solution to CDR. The 2 biggest companies in this space are shown on this slide here. Climeworks injecting CO2 into basalt in Iceland, and 1.5 doing it in Texas into sedimentary basins here. And these are currently doing very little, but have ambitious scale-up targets for how much carbon dioxide removal they can achieve. It's notable to me and worth mentioning that the bottom right figure there, the 1.5 company, is now a subsidiary of Occidental Petroleum. Oxy bought this. It was a startup, university spin-out and a startup company. It was bought by Oxy for 1.1 billion US dollars. And to me, this is an unambiguously good thing. Okay, this is a big oil and gas company saying, we want a bit of this market. We're going to come in and we're going to try and do negative emissions, and we're going to try and put the carbon dioxide under the ground. We need companies like Oxy, we need Equinor, we need Shell, we need BP, we need the oil and gas companies that we sometimes like to vilify to be part of the solution here and to be delivering the scaled up carbon dioxide removal that we're going to definitely need if we want to control climate. But there's one final thing I should say before I move on from direct air capture, and that is that thermodynamically, it's extremely inefficient to take carbon dioxide out of the atmosphere. As a scientist, I have to point out that it's much more efficient to take the carbon dioxide out of the chimney where you're burning your fossil fuels in the first place. It's at least 6 times thermodynamically more efficient, therefore uses 6 times less energy to take it out of the flue stack in your power station. So it's much more sensible to be doing this CCS for the gas-fired power stations as well, or before even we do the direct air capture. And CCS is also something we have to embrace if we're going to meet our climate challenge targets. So I'll stop with the direct air capture and move on to the other big technology that is proposed by the Committee for Climate Change to drive us to a balanced pathway here in the UK. And that's bioenergy with carbon capture and storage. Again, a little cartoon that shows you what we're doing. We grow biomass, chop it down, burn it, put it into a power station, make energy. So it's great, we're getting something positive out of this. We also make carbon dioxide, we capture it and put it underground. Meanwhile, we grow more trees. So we're using the same land to grow more fuel to do it again. Okay, so this is the technology that at the time of Paris, people thought was basically the get out of jail free card. They dialed up BECCS so high, saying we can do loads of BECCS, we'll take loads of carbon out of the atmosphere that way and we'll get some energy out of the deal as well. Definitely an unrealistic scale up at that time, but still a useful technology for solving our carbon dioxide removal challenge. So this is also part of UK planning and planning in Europe and elsewhere. There is a challenge though with all routes that involve growing stuff, chopping it down and using it for something. And that's there's only so much dead stuff you can use, or only so much living stuff you can chop down. And there's an analysis that I'll quickly run through here that shows you the limitations of this technology. There are several different approaches where people need biomass. They need dead organic material. BECCS that I'm talking about, biochar, spreading it on fields, or underground or submarine storage of organic carbon. They all need to have basically some waste product, or you need to grow it specially. And there's a limit to how much waste product there is, and that's run through here from forest, from agriculture, and from municipal waste. If you take all of that global supply of waste material from your food system and your energy system, what you end up with is something like an equivalent of 3 billion tons of CO2 removal maximum. That's useful, that's a big number, but it's still not the 7 to 9 billion tons that we need if we're going to achieve our known targets. And that's assuming a completely efficient system. And here in this analysis, I'm assuming that we don't grow crops just to burn them. If we're going to grow anything for fuel, we're going to use it for liquid fuels and put it in our aeroplanes rather than putting it into power stations. So that's the limitation on the biomass routes, but clearly this is a promising area. Oh, I didn't touch on this one. I should have said that at the top of this one shows you how some of the biggest companies in this area, they've achieved rather more CO2 removal, something like 40,000 tonnes from BECCS so far. So I'll come back to this image that I showed you once before, the cost abatement curve here. And I've spoken about BECCS and DACS on the far right-hand side here, the most expensive but also the biggest chunks of carbon dioxide removal in UK thinking. There is in the same colour, that's black colour, a little slither in the middle here, which is cheaper. Okay, and that's another negative emission approach. In fact, it's two of them bundled together. It's biochar that I've already spoken about and is limited by organic supply, but quite promising. It's also enhanced rock weathering. So I'm going to take you on a little journey on enhanced rock weathering now and spend just a little bit more time on this before I move away from the individual technologies. This is something that I've worked on and actually managed to continue to work on in Oxford, even while I was also working in government, so it's an area of interest. This technology works but according to the scenario that you see up here, we spread what is effectively a silicate rock. This is a very simple chemical rendition of a silicate rock onto fields, and it reacts with carbon dioxide to make the products on the other side of this chemical equation. Now, this reaction happens entirely naturally the whole time. The reason our buildings weather is because these reactions are going on and it's causing this reaction, but it's limited often by the supply of fresh rock materials. If you grind up rock very fine and spread it across your fields and the water falls on them, that will cause this reaction to dramatically accelerate, and then you might be able to take up a large amount of carbon dioxide. Now, this technology, this approach, works basically because you are releasing alkalinity into the environment. And this is a concept, this word alkalinity, that most people don't understand. Even geochemists get confused by use of the word alkalinity. Most people, if they come across the word alkalinity, they think about it as something they're cleaning their drain with, right? It's an alkaline solution you put into the drain. So I think I do have to give you a little bit of geochemistry here and talk about what alkalinity is. So I'll add a box to the bottom here. There are three forms in which carbon can exist dissolved in water, particularly in the oceans. That's where most of it sits. It can be notably in two forms that are ionic, the bicarbonate ion and the carbonate ion. And the amount of carbon that you can get into those two forms of dissolved carbon depends on how much positive charge you've got. So if you release more calcium 2+, as you do in this equation up here, or more magnesium 2+, or something else that has got positive charge, you are enabling the waters that those ions go into to hold more carbon. The ocean does this for us very well already. The ocean's got about 50 times more carbon in it than the atmosphere because it's a very alkaline solution. It's got lots of calcium and magnesium in it, so it holds lots of carbon for us. If we can increase the amount of carbon in the amount of positive charge, amount of calcium or magnesium in the environment, we can sequester more carbon in that environment. So that's what we're talking about. And I wanted to introduce that because I'll touch on it again when I talk about the oceans at the very end of my talk. So what about enhanced rock weathering? I've got three questions about this. So people are proposing this as a workable solution. There are many companies in this space. In fact, I should have pointed out the top three there, delivering about 9,000 tonnes of CDR so far. It's one of the more popular industries because it's relatively cheap. Is it actually going to work? So three questions there about whether it's workable and whether it's scalable. The first one is, do we actually believe we can scale it up as much as is being proposed? And if we look at today, the total amount of natural weathering is about 500 million tonnes. Literature assessments from models, particularly by proponents of this technology, say we might do up to 4 billion tonnes per year in this level. So that's an 8-fold increase of a global natural process that we need to cause by doing enhanced rock weathering. Is that really plausible? You can see that at a UK level as well, and I won't talk through this in detail, but at a UK level, one of my graduate students, Kirsty Harrington, did this great work to really work out how much natural weathering is happening in the UK and compare that to the estimates of how much we might deliver from enhanced rock weathering. And again, there's this massive difference in scale. So we'd clearly need to be very successful and make a big difference to our environment to change a natural process by a factor of almost an order of magnitude. If we do that, what does it do to the environment? And the second set of challenges in this technology are we have to get the stuff to spread on a field somewhere. We're going to have to mine it somewhere. That's not great for the environment. We're going to spread it to our fields where we grow all our food. Is that safe for our food production system? And we're going to substantially change all our natural water systems. It won't quite become mono-lake like this, but they will become more alkaline because we're intentionally adding alkalinity to our environment. And my third challenge of this technology, my third sort of technical, scientific challenge to the technology is to think, well, does it actually even work? Does it really reduce the amount of carbon in the atmosphere by a significant amount? I'm a geochemist. You'll have to bear with me a little bit on the geochemical details on the right here. But I think it's important to point out that we do need the alkalinity to be released. We've got to get it out of the basalt and put it into the environment. And if there are other places that alkalinity goes, if it absorbs the surfaces, if it makes secondary minerals, or even if it gets all the way to the ocean, which is the intention, then it doesn't achieve the same amount of carbon dioxide removal that we might have expected and for which we might have sold credits. So there is still a real careful job to do of understanding the technology and how much it can really deliver. Now, these sorts of questions that I'm posing about one of the technologies in particular, other experts might pose about their favourite technology. And it does rather beg the question, shouldn't these technologies really be regulated? Shouldn't we be thinking about how we police them so that we can innovate and we can drive carbon dioxide removal because we have to have it, but we can do that in a way that's safe and reliable? And there is a definite regulatory gap in this space at the moment. This is a summary, rather nice report that looked at regulation. This is a UK analysis showing you for different technologies, including the 4 that I've spoken about here, what regulation exists kind of accidentally, which polices aspects of the technology. So if I look at enhanced rock weathering on here, there basically is no regulation for planning and permitting, and there's very little for any aspect of it unless you're spreading waste. Basically, if you're spreading a waste material, it's stricter. You can spread anything else you want, basically, on your field. No one's going to stop you. No one's going to really check that it's actually doing any good. It's up to you and your risk on your field. Is that a sensible place for our regulatory environment to be in? And I'll talk about another example later on when I think regulation is actually too tight and limiting innovation. But in enhanced rock weathering, it's probably endangering our environment. So I think we have a real dilemma here. We need more regulation in this system, but we have a real double-edged sword here, and I think I can capture that on this slide. As an environmental scientist, we have a real conundrum at the moment. So we know that we have to do carbon dioxide removal at scale if we're going to sort out the climate challenge. And we know if we don't do that, the planet will get hotter, and that's bad for the environment as well as for human society. So we've got to do some CDR, we've got to do it big scale, but the instinct of most environmental scientists is you don't mess with the environment on a big scale. The precautionary principle says be really careful, really test out things slowly and carefully before you do anything large. So should we be pro or anti this set of technologies? I think that's something that many environmental scientists and NGOs are really wrestling with at the moment. But what is clear is we absolutely need to engage with independent research to test out the ideas, with the industry who are doing a lot of the application at the moment, with governments and with society. So that's kind of, I mean, I could almost stop here, but I do want to say a few more words before I do so. This is a dilemma that we need to face up to. And I think in that, facing that dilemma, we do need to think about a broader set of technologies that we might look to for carbon dioxide removal. And you can start by saying at a global scale, as a global geochemist, where could you possibly put the amount of carbon that we know we need to put, this very substantial amount of carbon? Most solutions at the moment focus on the subsurface, and there's plenty of capacity to put CO2 into the subsurface, something we might talk about later. The other place where I think, as a geochemist, there is plenty of potential for us to put CO2 is into the ocean. The ocean carbon content at the moment is huge. It's the biggest reservoir naturally of carbon on the surface of the Earth. Nearly all of it is one of those dissolved ionic forms that I mentioned before. And a relatively small change to that carbon system could make a big change to our atmosphere. So the idea that we increase alkalinity in the ocean, I think, is a promising idea that we should be looking at more. Ocean alkalinity enhancement works by taking an ocean that's already alkaline and making it slightly more alkaline. And then by doing that, you're effectively following this equation here, releasing positive charge so you get more bicarbonate. This is actually what the ocean will do naturally. It'll do it by dissolving limestone on the seafloor anyway, but it'll do it more quickly if we do it for it at the surface of the ocean. And we can make quite a substantial change with really a very small change to surface ocean calcium concentrations, much smaller than the sort of scale, the 8-fold change in weathering that I was having to invoke for enhanced rock weathering technologies. So we should be looking more at this area. But the oceans are a fraught space. They are somewhere where the public generally doesn't want to go. Public don't like playing around with the oceans. And we certainly have some challenges if we're going to pursue this. We have insufficient knowledge of the environmental consequences of really enhancing alkalinity. We don't really know how to measure it properly. We don't know how to regulate. There's not good regulation within our own waters. And at international levels, the level of unease about this is actually currently preventing the application of ocean alkalinity enhancement in the area beyond national jurisdiction. So we have a challenge at the moment that regulation is probably too tight, stifling innovation, stopping the research from happening, and stopping this technology from advancing. But it is advancing in some places. There are companies that are pursuing it both for carbon dioxide removal and for direct removal of emissions. So we need to look at a broader suite of technologies, and I've focused on one that I think is going to become important in the future. What happens if we don't succeed? What happens if we don't get enhanced ocean alkalinity or enhanced weathering or BECCS or DACS or biochar to work? If we fail to scale CDR, I think we are in trouble. And this shows you on the left the UK projections in the fairly near-term future and for how we get towards our net zero targets. And you can see the blue stuff that I've circled here shows you that there is negative emissions built into the UK plans for how we reach our carbon targets. And that's true in a lot of countries. A lot of countries now have negative emissions, carbon dioxide removal built into their plans for how we control climate in the future. So if we can't do that, if we can't do the negative emissions at scale, we either end up with this, a very much warmer planet that we're trying to avoid, and we know the catastrophic outcome of that, or we end up with what you see on the bottom right. Not big volcanoes. If anyone's doing a sciences here, I'm not suggesting there's a tendency for a hotter climate to lead to a volcanism, although there are possible ways that might happen in the very long run. But I'm not suggesting volcanism, but I'm suggesting something that mimics volcanism, and that is solar radiation management. The fact that if we can't control climate, and climate gets so warm that it's really uncomfortable to live or to grow food or to function in some parts of the world, just stopping the energy landing on the planet in the first place will start to seem like a fairly good solution. Better a world with solar radiation management than one which is 4 degrees warmer than today and impossible to live on. So if we move towards solar radiation management, there are a large number of significant negatives to this way of controlling climate. What you're doing is playing with a different part of the energy balance. If you reflect sunlight before it gets to the Earth by putting something into the atmosphere, you impact the shortwave radiation, whereas carbon dioxide is impacting the long-wave radiation, summarized by these bubbles on here. And the implications of that, although you might cool the planet by spraying something into the atmosphere, you might cool the average planet, you don't cool it in the same pattern that you've warmed it. You warm it through CO2, you cool it a different way, and you end up with a pattern that would impact different countries a different amount. So this means that we end up with a potential for geopolitical risk, countries threatening each other. There's an attribution risk about where did this cooling, where did this rainfall change come from? Was it your fault or was it natural? And there's also, it doesn't solve the CO2 problem in the ocean. Ocean acidification, which I haven't spoken about, will continue unabated. And the other challenge that people are worried about is that you're locked in. You have to keep on putting something into the atmosphere to reflect light away forever. Otherwise, you have a massive increase of climate when you stop, and what's called a termination shock. So solar radiation management has got a lot of negatives. It's a bad option. It may still become a better option than runaway warming that we'll get if we don't achieve carbon dioxide removal as well as our emissions reductions. And it is being increasingly talked about. It's being researched. These are some examples. It's even being commercialized at small scale, basically by a bunch of crackpots, in my view. But there are companies thinking it's more seriously about commercialization. And there is currently no international regulation of solar radiation management. The pieces in The Guardian talking about that were countered by a number of other Guardian pieces following that talked about the possible benefits of researching solar radiation management. So these technologies are increasingly being talked about despite the negatives that they have. So the pressure's really on. We've got to deliver on our carbon dioxide removal targets. So let me summarize. I've got 9 summaries to quickly go through here. We definitely need CDR. Hopefully I've convinced you that that is needed, and it's needed at scale, but the scale of how we achieve it is not yet very well understood, and there are some technical challenges to most of the technologies. There's definitely a danger, I think, at the moment that the market desire for carbon dioxide credits far outpaces understanding. And you see that by the number of credits that are being bought compared to those that are being delivered. We have a real challenge at the moment that people want the credits, but we don't actually know how to deliver them. And that's leading to quite perverse outcomes in the carbon credit markets. We have a lack of understanding of the regulation limits so in order to protect the environment during CDR scale-up. If we really do these things at scale, what are the negatives? And should we be regulating to stop them? We also know, and I think this is a challenge for people in the university sector especially, that many environmental scientists see this as a very big challenge. They're either starting a company because they think this is the right solution, or they're running away from the field and not getting immersed in the technologies and thinking about how we can solve the challenge. We do need more research, therefore. We need that to be in science, engineering, and in the social sciences, and we need to bring that work together in a way that can be achieved particularly well in universities like here in Cambridge. And one of the things we need to focus on is bridging what is currently a real gap between a technical understanding of some of these technologies and the socio-economic understanding of how we can scale them up and how they work in an economy. We definitely need CCS. That's controversial to some environmental groups, but it's absolutely clear we need it to get to carbon neutrality. We need it for a point source, and we're going to need it from direct air capture as well. We need to look carefully at ocean storage. I've talked about that at the end of my talk. We were going to need big companies in this space. And if you're someone who instinctively doesn't like the oil and gas companies, I'm afraid you just need to get over it. These are going to be the good guys who help to solve the challenge if they work in the right part of the energy spectrum and they're thinking about carbon dioxide removal as well. And if we don't achieve both stringent emission cuts and substantial carbon dioxide removal, I do fear that solar radiation management will continue its increase in the discourse and become ever more likely as a solution. So I'll stop there with thanks for listening.
Thank you very much, Gideon, for that very clear and super interesting overview, really, of the carbon crisis that we face. We will move to take questions from the floor, but before we do that, I'd like to invite two fellows from our college here to provide an initial commentary on their sort of thoughts on the lecture. And let me introduce them before I invite you to give your commentary. I'm going to begin with Laura. So we have Professor Laura Díaz Anadón, who has been with us here at St John's since 2022, but in the university since 2017, and she holds a chaired professorship at the Climate Change Policy Institute, I guess, here in Cambridge. She began her career as a chemical engineer through the universities of Manchester, Stuttgart, and a PhD here in Cambridge, but went on to study economics and public policy at Harvard. She is, I guess, a world-leading voice on many things related to climate, and I'm not going to read out all of the things that I could read out here. But, for example, she's a lead author in the 6th and the ongoing 7th IPCC assessment report, so the Intergovernmental Panel on Climate Change reports that will be known to many of you. And she has been twice elected vice chair and one of the 15 founding members of the European Scientific Advisory Board on Climate Change, created by the European Climate Law in 2021. So a justified expert to provide some commentary on what we've heard today. I'm going to introduce Andy as well at the same time before I invite you both to speak. Andy is also a fellow here and has been, I don't know how long Andy has been in Cambridge, but a while. Andy is a mathematician, studied maths as an undergraduate and a PhD at DAMT, which is the Department for Applied Maths and Theoretical Physics here in Cambridge. He now heads the Institute for Energy and Environmental Flows out in West Cambridge and is a leader on many topics relating to carbon removal and the environment. I guess some of Andy's current interests are energy transition, storage of hydrogen, removal of carbon dioxide and underground storage of carbon dioxide, which I think places Andy in an interesting position to provide some commentary on what we've heard today from Gideon's lecture. So that's enough from me. Laura, I'd like to invite you to provide your initial thoughts, please.
Yeah, thank you. I'll make 4 points. One of them is jumping off where I think you left it in your first comment, Gideon, which was on the market is overestimating what can be delivered on permanent removals, the technical ones you talked about. And I just wanted to mention that I think we can learn something from the past 10, 20 years of non-permanent removals, of the land-based removals, and how there was a big growth in the market. Over the past 5 years, research around the world, but also by me and my colleagues in the Department of Land Economy, have shown that the credits that have been sold through improved forest management and also avoided deforestation, the vast majority of them have not actually delivered emissions reduction. So this is a very real concern, and I think the fact that there was a lack of independent certification beyond companies that were benefiting themselves from certifying the credits is one of the main causes for why, in the analysis we did, we basically found that for the land-based removals, only out of the 972 million credits, 812 were not emissions reductions. So it was a very high degree of non-additionality. And just to give you a sense of the scale for this, those 812 million tons, this gap in achievement was larger than Germany's annual emissions. So these are not small factors. So I think we can maybe learn something from there in terms of the challenge ahead of us, which you very nicely laid out. I think the second point I would like to make is on this challenge of scale-up, right? How quickly can we get to permanent emissions reductions? And as was mentioned, most of these technologies were engineering solutions. And I think there are a couple of things that we can say from the history of technology. So first, we know that there's always the projects end up often being more expensive. New projects, new engineering projects tend up being very expensive, and then you have a little bit of a learning by doing process, right? So we can say that initially we'll probably see, and we're already seeing to some extent, this high cost, and then over time they might come down. The rate at which they come down depends on a few things. So it might depend on the technology itself, but it also depends on the degrees of standardization and learning in terms of how much project 1 is similar to project 10. So I think regulations and standards and learning across industry and sharing data and knowledge is very important in the process of scale-up to ensure that we have fast cost reductions, which is of course not the only factor, but it's an important one as costs are a big issue. We have seen, however, that some technologies learn faster than others. So even after we get over the first bump when costs come up, the rate at which they come down depends on things that go beyond standardization and sharing of learning. They can also depend on the technology itself. So we have seen that things like nuclear power, things like bioenergy, so burning biomass and generating electricity, those costs have not come down as fast as the cost of solar panels and solid state lighting. So there may be some of these engineering and solutions that just because they're more modular, simpler processes, you do more of them, you enable more learning, may have a higher potential. And I think that's also something that should be considered at the UK policy scale, but also at the European level. And the final point I wanted to make, and this is something that we discussed in our report that we did in this European Council for the EU, we recommended a few things to enable this scale-up. The most important one, in my view, is improving our ability to track and certify both the cost, the additionality, and the environmental impact. So I agree that this is a huge role for government to make sure we don't have the same debacle that we had in forest offsets. But that's not enough. I think in addition to this, what we've learned from the big cost reductions and deployment, which actually outpaced expectations in solar and wind, solid-state lighting, is also having a clear set of policies that create certainty so that people can invest. So that's something that, for example, has really hurt things like carbon capture and storage and demonstration projects. And the third thing, beyond the being able to certify the environmental impacts and the additionality and the cost, and also creating a system where companies know they can go into the market because they can learn and over time get better, is having a separate target for these permanent removals that maybe eventually gets integrated into an emissions trading scheme, which the UK has and the European Union has. So this is a very clear example in my mind of an area of policy that does require multiple roles for governments to enable the safe, sustainable, and efficient use of these technologies, some of which will be essential. Thank you.
Thank you very much, Laura. Andy, yes, thank you. Andy, I'd like to invite your comments, please.
Thanks very much. Well, first of all, I'd just like to thank Gideon for a fantastic lecture. I think we heard very, very clear description of all the different approaches to CDR, the challenge and the materiality of CDR at the moment. And I think this sort of points to the gravity of the challenge, just how big a challenge it is. And I really enjoyed your discussion of how much coal we'd need to actually store this. I normally talk about it in terms of how many Wembley stadia would we need, and it's about 1,000 or 2,000 Wembley stadia to put all the CO2 in we need to capture every year. So we'd have to build 2,000 stadia every year to do this till 2100. And I just thought I'd mention make two or three observations. The first is that this is really a global challenge, and today globally, about 83% of energy is fossil-based, of the global energy. And as we decarbonize this energy source, it's going to take decades, 2 or 3 decades at least, to actually decarbonize. And so there's going to be a continuous emission of carbon from those fossil fuels that we continue burning as we build wind turbines, as we build solar panels. The factories that build them need power. And so this is a transition. It's not something that we're going to change overnight. And all those emissions will accumulate in the atmosphere because the carbon remains in the atmosphere. And so I think we need to also think about the CCS, the carbon removal from power plants and industrial plants, as well as the CDR from a lot of the approaches Gideon was talking about, because those are going to be additional emissions that we need to worry about. And as Gideon said, they're coming from very concentrated sources in chimneys at power stations or cement factories, where it's much more energy efficient to capture that carbon. So I think for the next decade or two, we need to be focusing on that sort of carbon capture, as well as capturing it from these other approaches. And we can also learn from what's going on in the carbon capture and storage industry to help inform how some of these other technologies might scale up. And if we look in the UK, we've got 2 big projects going on. We've got the Endurance field in the North Sea, and we've got the HyNet field in Liverpool Bay. Each of those are going to be storing 4 or 5 megatons per year. So that's orders of magnitude bigger than lots of these other technologies. That's going to be safely stored 2 kilometers below the surface. That is regulated, and there's a lot of work being done to look at the risks. And a lot of these new technologies also need a regulatory environment to actually understand the risks involved. Because if we're investing large sums of money to do material amounts of storage, we actually need to manage the risks associated with that to make sure it's well spent and it's a good use of resource. So the other thing that is interesting is that when you try to do very large-scale carbon capture and storage, it's actually very difficult. And it may seem, so in some of the models, these appear as boxes, and as Gideon mentioned, it's with carbon capture and storage is put in as a box to do negative emissions. But actually assembling the carbon that's being emitted at power stations or at factories, putting it into a network, and then pumping it off to the store is very complicated because you've got security of supply of the carbon into that transport network. You've got someone needing to manage the transport network. You need some surface storage to buffer the supply with the demand of the people storing it in the permanent store. And building that is very complex, and we need to learn how to do that. And we obviously need to scale this up enormously. And I think there's lessons that can be learned from how big industry are doing this in terms of how these other areas will scale up. So it's a very, very complex problem, but I think there's lots of learning. But I think we should sort of try and embrace and encourage everybody to be involved in this because big industry, particularly the big energy industry, have been doing a lot of work on this and understanding how to manage risks and how to actually build these financial or these commercial enterprises that pull together capture, transport and storage. And so I think there's a lot of lessons from that. But I think my main point I go back to is that this is really a global challenge. And if we're looking at where the carbon is emitted today, in terms of how we're going to do some of this carbon capture, we really need to be thinking globally about what the emissions are. And when we talk about net zero, I think one thing we should reflect on is that net zero is net operating carbon. It's not the capital carbon emitted in making some of the products. And we need to be thinking about how we audit or account for the carbon in the things that are made. So we've offshored lots of our industry, and the carbon is now being emitted elsewhere with largely fossil-based fuel to power that. And somehow the accounting system for the whole of the carbon system might merit sort of a rethink in terms of doing both operating and capital carbon in the way we account for things. So I'll finish at that point, but I would like to thank Gideon for a super talk.
Thank you, Andy. Gideon, I'd like to invite you to respond to either of the panellists, actually, or to pick out any points that you would like to respond to.
Yeah, okay, good. And I don't want to keep questions from the floor too long, but just quickly, Laura, I thank you for your analogy with some other technologies. I think that's a very good way of looking at it. The optimist in me says that if you look at something like photovoltaics and the pace at which that market has grown and the pace at which the cost has come down, at the most optimistic sort of analysis of photovoltaics, if you apply that sort of curve to CDR, we can do it. The scale up is possible according to that analogy by photovoltaics. But that's an optimistic view, and some of the other technologies have scaled much more slowly and the costs have come down more slowly. So I think we do need to back a lot of different horses here. We have to be looking at multiple technologies, not just one or two of them. And we need to be looking for those that will scale more successfully. And I absolutely agree with you that we need to be thinking about the regulatory environment that goes around them so we're confident that the negative emissions we get are genuine, they're permanent, and that they are not causing significant environmental harm. So I think that's a nice analogy. And Andy, thank you for your comments as well. And I particularly enjoyed your describing of a carbon system which will need to be built. We forget how complicated the system is that we've used to take carbon out of the ground and to put it into the atmosphere while generating energy. We're going to need a system that is equally complicated and large scale if we're going to take carbon out of the atmosphere again and put it back somewhere securely for a long time. And your example was very well taken, so thank you for your responses.
Okay, thank you very much. Those are obviously very interesting commentaries and a response. I think what I'd like to do is open the floor to questions, if I may. And looks like Simon has his hand up here at the front very eagerly with a question.
Thank you. Thank you, Gideon, Andy and Laura. Wonderful set of presentations. Two or three points. One is the photovoltaics story principally one of the outstanding commitment of the Chinese government to that technology, or am I misunderstanding what's happened? In other words, this wasn't so much, this was to do with not the normal processes of the market, but a government seizing strategically and making that work. So that's one question. Another one is whether it seems like, Gideon, you kind of gave us a dream scenario of ocean alkali technology as being in, you know, if it could somehow happen, that would be your dream. But you concluded by sort of saying that solar radiation capping you feared was the bad fairy that was out there. Is that something to do with short versus long term? It slightly relates to my first question. Is it because there's something about the solar radiation thing that suits the capitalist free market to get on with and make money out of, even though it may not actually work, whereas the alkali thing is a altogether bigger thing that needs something equivalent to the Chinese government to deal with?
I'm happy to talk about
Do you want to do the first one? Yeah, yep.
Yeah, so I wouldn't characterize it like that at all. So it's not the Chinese government that said we're going to just fund solar and that's why costs have come down. The story really goes back much further in time, goes to Einstein, the photovoltaic effect, goes to Bell Labs, the first cell, goes to the Sputnik space program and NASA doing, you know, putting cells. Then we started getting subsidy programs actually in Europe and in Japan. So we had the 10,000, like 100,000 roofs program, solar program in Japan in the late 90s. Then Germany played a major role with the feed-in tariffs in the 2000s. In fact, you know, that was the big thing that in that time period, other countries followed, created subsidies. So the costs were falling down at 20 to 25% per doubling of production for decades before China started actually getting into the manufacturing business there. And what happened was in the 2007 or so, you started getting, it wasn't a state-owned enterprise story at all. It was founders, Chinese people who had been trained in Australia, the US, various places, went, got funding from abroad, were able to access generic support for local development in China, and then they created these companies that are now big manufacturers. And after China already had 50% of global market share of solar panels, that's when China started putting feed-in tariffs and that sort of thing. So yes, it did contribute significantly to the cost reductions we've seen over the past 10 years, but the story is far from a just China story. There's a great book by Greg Nemeth on this. I've written also about the lithium-ion battery case, which is also one of really fast cost reductions that is not just a China story. Same with solid-state lighting, it's not just a China story. It's subsequent, initially uncoordinated, but then, you know, learning by doing in policy that led to these big technology cost reductions. But I think the key thing is that that rate of cost reduction is very high, and I don't think we can assume that rate of cost reduction will happen for all of the different CDR options. So yeah, China is great, it's producing a lot, it's installing a lot, but it's not what has caused this miracle.
Shall I do your second question? Okay, so, well, I'm positive about ocean alkalinity enhancement because I think fundamentally that's what nature would do. It would just take 1,000 years to do it. But if we do it faster, then that will be a secure and stable way of storing large amounts of carbon in a reservoir where we think it will nicely complement the underground storage. So I'm not advocating we should stop doing the sorts of technologies that Andy was talking about at all. We should carry on with those. We should add ocean alkalinity enhancement to that mixture. We don't know enough about it to pursue it at scale yet, but I think we should try and push towards that quite quickly. So I think it's safe environmentally and stable. That differs significantly from solar radiation management, which is not something nature would do intentionally in response to climate. It might do it accidentally by a volcano occasionally, but it wouldn't do it as an intentional climate response in the same way as ocean alkalinity enhancement. It's also balancing a very different part of the energy budget, as I discussed, with implications that will cause, it could cause the monsoon to fail, for instance. So the temperature will be cooler around the world than it would be otherwise, but the monsoons failed in India. What are the Indians going to think about that, and who are they going to blame? So you end up with these possible geopolitical tensions arising, and in a way that you're not actually solving the problem, you're just putting a sticking plaster over it. The reason I fear it is it's much cheaper, and you could achieve it with much less economic costs. So if a country, or even basically a very wealthy individual, decided that they felt it really was time to control climate, that would be the easiest lever to pull.
Okay, thank you very much. Further questions? Thank you. Could you speak into the microphone?
What do I press?
Just speak. And it will be
Just speak, okay. I'm just here out of interest. Thank you for a very interesting hour. I just wanted to ask about the low energy concrete that you mentioned earlier on in your talk, and whether any scaling up with companies like Occidentals, but in that market, is being done with concrete, and how buildings are designed, and what is done with the waste concrete that is present in so many conflict areas.
Thank you for the question. So, concrete and lime production makes about 5% of our global emissions at the moment. So that our production of when you make cement, you have to emit CO2 as part of the process. So it is something we need to focus on. There are technologies by which we can remove CO2 during the production, and then you have to store it somewhere. So you end up with challenges that Andy was talking about of how do you have a carbon management system to put the CO2 underground. But those are technologies that we could pursue, and some companies are chasing at the moment to try and make cement and concrete less polluting, less warming. It's also very clear that if you replace concrete from your building system completely and use wood instead, it's hugely beneficial. You chop down some trees, you embed them permanently in your built environment, and then you've got space in which you can grow new trees. And so you've displaced the cement, you've kept the carbon that's in the trees, and you're growing more trees. So there's multiple benefits of using wood for building and replacing cement that way. What we can use old cement for, and it does automatically consume CO2 in the same sort of weathering reactions that I showed for natural silicates. The extent to which it does it on its own, it takes a very long time and doesn't do it completely. We may be able to enhance that, and some people are talking about spreading cement on fields as an enhanced rock weathering approach. So we might be able to use it as a waste that we can get some carbon benefit from as well. These are being looked at by some companies.
Thank you very much. Thank you for the response. Thank you for the question. Any other questions from the floor? Yes, multiple questions. One at the back there.
Hi, thank you for the great talk and for the panelist contributions. My question is in regards to the regulatory and permissive hoops you have to jump through to employ geoengineering solutions for for CDR or MCDR. We've been doing geoengineering for decades, just the polluting and, like, for example, claiming land for agriculture use, or like even for commercial building and building up our urban centres. What is the cause, in your opinion, between the seeming, the apparent disparity between the ease it is to, for example, start a farm versus start a CDR project? Does that make sense? Or is it a cultural difference between geoengineering to burn fossil fuels compared to try and take it out the atmosphere? It seems to be easier to employ technologies that release greenhouse gases than it is to take them out.
So I think for most of the time that would certainly be true. Quite recently, there's actually quite a lot of venture capital in carbon dioxide removal technologies. There's more money than there are companies that know how to do anything useful with it at the moment. So at the moment, finding funding for your company is often not the limitation. It's having the idea and having the ability to pursue it and to scale it up that's often the challenge. And in some situations, there are regulatory constraints as well. I think that's particularly true in the ocean environment, but there are regulatory barriers elsewhere. So what's needed is persistent investment. So at the moment, there's investment, but we don't know how long it'll last. We need clear market signalling, and that includes from governments as well as from business, that they're going to want these products and they're going to need them. I think that's happening at national level. You see it in the UK plans, and it's definitely true in the European plans as well. And we're going to need careful regulatory change to make sure that things are being encouraged but not causing harm. And probably we're going to need some government spending in the form, which could take the form of feed-in tariffs that we were talking about earlier, or could take the form of research spending, but something to try and kickstart some of the markets. So those are some of my thoughts. I don't know if others have got follow-on thoughts.
Yeah, I think, learning from, let's say, the other experiences, If there isn't a guaranteed demand and also it's guaranteed that you're going to make money, we're going to have a situation like what we've had with a lot of other projects. If you don't have a separate market for some of these technologies that are very different and more expensive, then it's not going to happen, right? So that's why we haven't really seen CCS, right? It's right now more expensive than a lot of these other technologies like wind, solar, and these sort of things. So it's not coming under the emissions trading scheme because it's too expensive. The solution that was created in the UK for wind was that when the wind auctions were just wind in general, they were always won by onshore wind. There was a separation into offshore and onshore wind, and then you started getting on the learning curves for both. So I know that there's this idea that technology neutrality is a great principle for policy making. In reality, you sometimes need to depart from it, and actually in practice, when you have technology neutrality, you're favoring the incumbents. So I think that's and that's why in the EU climate board we said, well, there should be a separate target for permanent removals. Then there can be competition between these different options, right? And that target should also come with funding that enables people to make money out of it. Right now, it's just corporations that are buying, investing in these technologies, but it's totally unregulated and guaranteed, and maybe they pay for it, but then nothing happens, as you very nicely said. So I think right now we don't have a system that is going to allow us to learn about the risks and the scale up and the cost of these different technologies. We just need more certainty and more investment and regulation.
I think that's an important distinction, which was on my slides, but I don't think I spoke to, is at the moment the whole of this market is a voluntary market. So it's basically companies saying we want to reach net zero, we'll buy some credits and we'll invest. But there is a move towards a compliance market where companies are required to do it by regulation and law in their countries. And that is going to require a lot of the activities that we've both just spoken about, including making sure the regulatory environment and the incentive system and the law is set up appropriately.
Thank you. There's a question down the front.
Hello, thank you all so much for the fantastic talk. I just have a question in regard to thinking about the storage of direct carbon capture, and specifically thinking about, although there is ground everywhere where we could hypothetically store this carbon, it's not all equally injectable, right? And so I guess I'm curious as to whether or not you think there is a theoretical limit or cap as to how much carbon could feasibly be stored underground, and is that a limiting condition as we're considering this?
This is one for you, Andy, for sure. I said 12,000 gigatons in my slides, but you may disagree. Are you the expert?
Yeah, I think that's a very interesting, very good question. There's a lot of aquifer pore space, and we're talking about depths of 1.5 to 2 kilometres, and there's a lot of pore space globally where we could do this. There's only a few projects where this is actually happening at the moment, and the more you do, the more you learn about the potential storage capacity. So the UK continental shelf has an enormous amount of storage for many, many decades for the UK emissions and longer, but it could be bigger than that. I mean, the present estimates that the British Geologic Survey have done for the UK continental shelf assumes you can access, I think it's 3% of the pore space. So these rocks are about 20% pore space. So it's like beach sand that's been compressed and buried to 1.5 kilometres. 20% is space where you can put the CO2. If you imagine you have a reservoir and you're going to try and target 3% of those holes, that's not very much. So there's an enormous scope for new technology, new ideas to improve that. But it's only by doing it that we'll learn how to do that. And if you can increase it to 4%, that's a 30% increase in the storage. So there's an enormous space of research to be done really to understand this, and there's a lot of work's going on globally to do this. So yeah, but there's plenty of pore space available for all the emissions for many decades.
Might you make a distinction between point source emissions versus CO2, which is pervasively throughout the atmosphere, distributed throughout the atmosphere, in terms of how much you would be able to capture or how you would go about capturing it? We heard about a thermodynamic penalty in the lecture, for example.
You could put you've got to have your point sources close to a reservoir. And when you've got reservoirs that have got good point sources, you should do direct CCS from your point sources. where you've got good reservoirs a long way from any point sources, then perhaps direct air capture is well sited there. And that especially if you've got a ready energy supply, because direct air capture is all requires energy. So if you've got a large amount of area where you can put your photovoltaics or your wind to drive the system, and you've got a reservoir, then that could be a good place to do direct air capture.
Thank you. There's a question. Oh, lots of questions. Sorry. Question over here first.
Well, thank you for your wonderful talk. I really enjoyed it, Gideon. Just one question from an early career researcher. You know, a lot of time we have to present some data about the trend of energy sectors, different energy sectors. What's the most reliable source to gather the data? I saw your trend, and for instance, I'm looking at buildings, and the trend was slightly different to what I saw in International Energy Agency report recently released, because the expansion of digital infrastructure shows there is a slight increase in the last year or two. Mm-hmm. So I just want your advice to what source of data you would recommend to look at, because I know there are plenty, and yeah.
I think others may have comments about energy specifically. The data I showed you was the CO2 emissions. I think you're talking about one of my early slides, CO2 emissions from various sectors. That comes from the Climate Change Committee, and that's definitely a good source to go to. It's very authoritative for UK emissions. The graph runs out a year or two in the past, so it hasn't got the last year or two in what I showed you, but that's a good place to go. It is true that the major data centres are causing a change of emissions in the UK as elsewhere at the moment, so it's a good point. For good sources of energy information, I'm probably not the right expert, but I don't know if others here might know more.
I guess in the UK, if you want to look at just the UK energy consumption, there's the government have a website, the Duke's data, DUKES, and if you look on that, it just tells you the actual emissions for the last few years and the sources of the energy. There's a number of international reviews of global energy consumption, and they're all, the numbers slightly differ, but there's a sort of annual statistical review of energy, which I think is run by the Energy Institute in London, and that's quite a reliable source.
And again, if you're looking at Europe, there's also data from Eurostat and the European Commission on other countries, so it depends on where you're looking at, but I agree with what was said, of course.
Thank you. There were hands up. We've probably got time to take maybe one more question.
We could take a couple and then we could choose which one to answer. Make our life easier.
Yeah, I like your approach.
Yeah.
Thanks to all of you for all this information. I have a question, or I would like to hear your opinion on, is there a discrepancy, or what is the discrepancy between, because we've all learned it's a very complex problem and it's a global complex problem, so what's the discrepancy between industries and bigger countries who continue, or we all put out CO2 in the atmosphere still, and then there's efforts of taking it out of the atmosphere, but what's the discrepancy between what still goes out versus what we can sequester, and what's our best guess on if we can actually get to the point where we manage to shovel in more into the soil than we blast out into the atmosphere? Yeah, I would be interested, especially now because some countries stop to have limitations on CO2 emissions, for example, or...
Well, the very simple fact that perhaps we should reiterate as we come to the end here is climate will carry on warming until we reach net zero. Okay, the comment net zero, and people are starting to say, well, this is a phrase we don't really like anymore, we don't believe it. That's just a scientific fact. We've got to get to net zero if you want the climate to stop warming, which we definitely want to happen. So we're going to have to do the balance that you've been talking about. We are nowhere near it yet. We're emitting 40 billion tonnes of CO2 into the atmosphere at the moment. We've got to get that down to net zero. And we've got to try and do it as quickly as we possibly can, and we're going to need CDR in that mixture.
I mean, it might be worth mentioning that year on year now, the carbon emissions are increasing. Global energy consumption or global energy demand is increasing by 1 to 2% a year. And the growth of renewables is not keeping pace with the growth of energy demand. So, these are big challenges. So really big challenges. But yeah, absolutely, what Gideon says. We need to get going on all this.
Yeah, I would just add that so the UK has a net zero by 2050, the EU has a net zero by 2050, but right now when we look at the, we would have to all get to net zero by 2050 essentially, right? So, and if we get to net zero by 2100, then the temperature is going to be much higher, right? So that's just, the net zero is by when, and that really matters in terms of what we end up in. Right now, governments committed under the Paris Agreement to submit their nationally determined contributions and update them. Not everybody has done it. The US has, of course, left the Paris Agreement, but the submitted NDCs are not consistent with, certainly 1.5. They're more in the range of 2.3, 2.4, the median with uncertainty around it, as was shown in the slides. So why is there a disconnect between what many scientists and the IPCC and the Paris Agreement said we would do? Well, there's the economic incentives in the market, there's behavior, there's our infrastructure, and it's hard to imagine that things will change if there isn't an even bigger effort by everyone, people, governments, and corporations. And one thing to say about the corporations is that these voluntary markets, right, is companies saying we're buying credits from DAX or BEX or whatever, right? So what is in their interest? To say they bought those credits and their emissions are lower. So they don't really care, right, if those things happen, because they can already say that they bought the credits. So we just need a system that has the right signals, incentives, and information.
Thank you. Thank you all. I think that feels like it's probably a sensible place or a sensible time to draw this to a close. I know there were more questions at the back, and there is a drinks reception downstairs in the foyer, and I'd like to encourage people to come along to that and continue the discussion down there. Maybe you can find someone or ask one of the panelists downstairs over a drink to try and continue these really important and societally planetary important questions that we're trying to get at here. And I think perhaps a good point to end on is really the summary points that we heard from that last response there, that climate will continue to warm whilst CO2 keeps going up in the atmosphere, yet energy consumption keeps going up year on year. These are major issues that will need to be addressed through multiple pathways, which is, of course, what we've heard throughout both the talk and through the panelist discussion. And so really what I'd like to do is thank Gideon enormously for the very clear and really inspiring, thoughtful talk, and both Laura and Andy for their interesting and thoughtful responses and difficult responses, really, to this globally challenging problem that we all face together. And of course, thank you to all of you for being here as well. So maybe a round of applause for one last time for Gideon and the panelists.